I am David Jeffrey, and today I'll be speaking on a problem in pure mathematics which I explored using Maple. The topic is completely monotonic functions. Most students of calculus have come across the term monotonic. That is a function which is always increasing or always decreasing on a particular interval. When we add the word completely in front of it, we require that monotonicity property to apply not only to the function itself, but to all of its derivatives. And we require all derivatives to exist as well. As an example, I've given here e to the minus x. You notice that if x is equal to 0, e to the minus x equals 1, and then it decreases monotonically to 0. If I take its derivative, I get minus e to the minus x. When x equals 0, it's now equal to minus 1, and the function will now increase monotonically to 0. When I take another derivative, so I'm at a second derivative, again I'm back to e to the minus x, so it will decrease monotonically from 1 to 0. A common convention to multiply every odd derivative by minus 1, thus turning all the functions and the negated derivatives into positive functions which are monotonically decreasing towards 0. This gives us the definition at the bottom of the page. A function f is completely monotonic if f has derivatives to all orders and it satisfies minus 1 to the n derivatives of f, and that has to be greater than 0, and that has to apply for all x. Notice that although the term monotonic describes both functions that increase and functions that decrease, completely monotonic, after we add in the minus 1 factor, applies to functions which are only decreasing continuously over the interval. Alzer and Berg proposed a family of functions, as you see here. The question is, for what values of a will this function f be completely monotonic with respect to the variable x? If you look at it, you will recognize 1 plus a over x to the x. You may remember that from your first year calculus limit questions when, as x goes to infinity, that 1 plus a over x to the x in the limit equals e to the a. So here we have e to the a, the limit point, minus 1 plus a over x to the x. One of the things that may not have been pointed out to you when you studied this limit is that 1 plus a over x to the x approaches the limit from below. Therefore, e to the a minus 1 plus a over x to the x will be a positive quantity, and it will tend to 0 as x tends to infinity. Will this be completely monotonic for all values of a? That's the problem, and now I shall switch to a Maple worksheet to show you how I tackled it. What I'm going to show you is exactly the path I took to learn about this problem and make some progress on it. So we start off. Now the first point is that I actually knew very little about completely monotonic functions when I took this problem up. So my first task was to teach myself about completely monotonic functions so that I could get some idea of how to tackle this question. So let us start. Maple is very good at plotting things. Plots are always a good way to learn about functions. So here we have a plot. I've plotted f against x for a equals 2, a equals 3, a equals 4, and a equals 5. And you see that in each case the function is clearly monotonically decreasing. So how about we plot the derivative instead of the function and see whether that tells us anything new. And I forgot the minus sign, so that is just to remind us that we start with negative values and increase towards 0. We notice that the derivative, the red curve, is monotonically increasing, as is the green curve. But look, the blue curve and the black curve are clearly not monotonic. So we see this is what is the purpose of this completely monotonic property. A function itself can be monotonically decreasing or increasing, but that does not necessarily apply to the derivative. So let's put in the minus sign and look a little bit more closely at a equals 4. Notice my vertical scale has now increased. It's from 3.85 up to 4.15, and we see this marked departure from monotonicity. So we can ask ourselves, well, what would happen then if we took more derivatives? So now, here I have minus the first derivative plus the second derivative is even, so I don't need the minus sign, again for a equals 4. Now you notice the vertical scale has changed. Now it's going from 0 to 8, so that rather spectacular departure from monotonicity looks a lot less on this larger scale. And the green curve is now the second derivative. So the second derivative, not only has it departed from monotonicity, it's not even positive everywhere. It dips below the axis. So maybe the key to understanding the problem is to take more derivatives. So that's what I'm going to do. I'm going to take now 3 derivatives, as you see, with minus signs on the odd derivatives. I've also lowered the value of a little bit to 3.6, just to see how that affects things, and I plot that. Well, at 3.6, we notice that the first derivative, the red curve, is now monotonic again. We notice that the second derivative, which previously at a equals 4 became negative, dipped below the axis, is now just a little bit above it, and the third derivative is now the one showing the more marked departure from monotonicity, also becoming negative. Now, we can ask ourselves the question, well, what is the process whereby a function changes from being monotonic to not monotonic? How does it pick up that blip that we saw, first derivative at a equals 4? Well, clearly it must go through an inflection point and a horizontal derivative. That would imply that there must be a point where the first derivative is going through a horizontal inflection point. That would imply that the second derivative will just touch the axis and the third derivative will be 0, because the second derivative gives you the slope, the third derivative gives you the curvature. Also, we notice that when a equals 4, the green curve goes slightly below the axis. At 3.6, it's slightly above. So presumably there is a value of a between the 3.6 and 4 when the green curve will just touch the axis. And according to our understanding, that point where it touches the axis will coincide with the point where the blue curve crosses the axis. In other words, they will both be 0 at the same point. Can we find that point? Yes, we can. What we'll do is we'll use the maple fsolve command. So here I have handed to fsolve the second derivative and the third derivative, 2 equations, 2 unknowns, x and a. The critical value is, as we guessed, slightly between 3.6 and 4, 3.6912, and x is 0.487, which again is very close to what we see above it. So let us take that value of a, put it into our functions. I see a typographical error there, which I failed to correct. I shall save it for next time. And let's see what we get. So here is our graph, and as you see, the green curve touches the axis, the blue curve crosses the axis at exactly the same point, and if we look up here, perhaps with a little bit of imagination, we can see a horizontal inflection point as we expected. So now we have a way of finding the critical point and the critical value of a in which the first derivative changes from being a monotonic function to being a non-monotonic function. The obvious question is, how will this change when we try the same procedure with higher derivatives? So let's do that. I'm now going to calculate a third and a fourth derivative. I've printed out the fourth derivative just to remind us that as we take more derivatives, we have to expect the expression describing that derivative will become longer and longer. So we must bear in the back of our mind that as we explore these derivatives of f, we're going to have to keep an eye on our memory usage. So now that I have the third and fourth derivatives, I can use that to find the critical point of the second derivative. So I'm going to f-solve that. Now, f-solve has done a good job so far. One point I did not make, I shall go back and make it now. Numerical analysts will tell you that trying to find the place where a function just touches the axis rather than crosses it is a more difficult numerical problem than finding a place where a curve crosses the axis. We saw that before f-solve had no trouble, but any iterative numerical scheme performs better if you give it an initial estimate of the point. Many textbooks refer to this as an initial guess. But I'm not guessing. I know where it ought to be. So with that initial estimate, again, Maple has no trouble finding the critical point. And we notice that A has decreased a little bit. Previously it was 3.69. Now it has jumped down to 3.13, and x, which was 0.48, is now 0.91. Let's try it again for the third derivative, which requires that we calculate a fifth derivative. So now we're going to look for the zeros of the fourth and fifth derivatives to find out the critical value of the third derivative. Let's just plot that, and here we have it. The black curve is now the third derivative, red curve is the fourth derivative, and the green is the fifth derivative. We notice two other things. Firstly, all of the curves have shifted towards the right. Our original plots went from 0 to 8. Here we're going from 0 to 0.5. So the functions are getting smaller as we increase the number of derivatives. So let's keep going. Charge through higher and higher derivatives. We notice that the value of A is decreasing at a slower rate than it was before. So there I've calculated my way to 30 derivatives, which of course required 32 derivatives to find the critical point of the 30th derivative. At this point, it occurred to me that I ought to check on the numerical procedure itself. How much is the rounding error going to vitiate my results? That's not a great problem for me. It seems to be a problem for me to spell the word ability. I use Maple's ability to work with more precision. And now I can repeat the same calculation at the higher working precision. So the good news is, even with 30 derivatives, we've only lost 3 digits out of 10. So it seems that f-solve is relatively stable. So now is a good time to stop computing and start thinking. It's a fact, at least with me, that computing can easily take over thinking. Here I extract from those saved results all of the sequence of values of critical A's, and I'll plot them. So this shows me what I had already observed informally, that the critical value of A is progressively decreasing as the number of derivatives increase. And also we see that the rate of decrease is going down. What we need to get the critical completely monotonic value for A is an infinite number of derivatives. I can't plot out to infinity, but what I can do is, instead of plotting against the number of derivatives, I'll plot against 1 over the number of derivatives. This straight line is crying out to be fitted with another straight line, approximate straight line. So that's what I did. I just calculated a fit, and there it is. I'm now plotting from 0, whereas before I was plotting from 0.05. So we see the red curve is the curve we have just been calculating. The blue curve is my fit. You can see the red line stops here, and here I have plotted all the way to 0. So we see my extrapolation intersects the curve here at about 2.3. Up here I have the value of the fit. A fit is pretty close to 2.303. So I can ask the question, how many derivatives will it take until I get down to 2.303 according to this extrapolation? And it's unlikely, even with Maple's power and modern laptops with their gigabytes of memory, that I'll be able to get to 5,000 just by this simple-minded approach. This table shows n is the number of derivatives, AC is a critical value of A at which that derivative changes from monotonic to non-monotonic. The scheme which I used to calculate 1,000, 2,000, up to, you see, the last entry is 100,000 derivatives is described in the paper. I'm not going to try to describe it in this short talk. Let's look at how AC behaves. So you can see it is decreasing rather slowly and appears to be converging. So with extrapolation, A infinity was this 10-digit number here. And with that number of digits, I can now ask various systems, do you recognize this? Maple itself has the identify command, and online there are things such as the Plouffe inverter. Neither system could identify this number with anything previously known. A generalization of the problem, just a quick word about the future. Altenberg posed a more general problem. You see e to the a minus 1 plus a over x to the x minus b. So they have added a second parameter to the problem, a and b, and with my students we are at the moment extending our numerical investigation. With that, thank you very much.